section Jessell. I don't know how Steph arranged to get him here, but
He had a layover.
Thank you.
I think he just had a few hours in Johannesburg, and we said, come on through. And where are you going to?
From Ghana to Perth.
Okay, so right, from Ghana to Perth, Australia, and he works at University of Western Australia. And we've been working together for quite a number of years on various projects, mainly through the supervision of Ghanaian PhD student. And so it's been really exciting. I've actually gone to Ghana myself, not yet to Australia, but I hope, yeah, not subtle, am I? I'm hoping to get there at some point. And I guess over to you. And
Thank you.
welcome.
Yep. I'm going to be talking about lots of people's work here. Some of them are listed here, and I'll list the rest of them at the end. I'm going to be talking about West Africa, and here is the earliest compiled map of the geology of West Africa. It comes from 1933, and it shows you everywhere from what is now Morocco through Mauritania, Senegal, Sierra Leone, Liberia, Cote d'Ivoire, Ghana, Togo, and also Niger, Burkina Faso, and Mali. All these countries contain bits of the same geology. So one of the challenges we have is that no one country has all the answers. And the second challenge we have, which is a very big challenge, is that every country in West Africa has a neighbor that speaks another language. So communication between all these countries is quite hard. The most recent regional compilation comes from 2013, and it covers West Africa. So here we have an Archean block in the south, the Paleoproterozoic block beside it, an Archean block in the north, Paleoproterozoic block beside it, and then in between we've got this big sag basin, which is Mesoproterozoic. The bit that we've done most of our work in is this bit in the south, and that's purely for pragmatic reasons that it's taken us 20 years to do that bit. So, and we haven't finished. So what we're looking at is trying to understand the geological evolution of the region. We're trying to understand the reason why the gold is where it is. Only gold, just because we've been sponsored by a lot of companies, and almost without exception one or two, those companies are looking for gold. So it makes sense to look for gold with them. There are lots and lots of ideas about how greenstone belts work. And I'm not going to go into all the details here, but some of them assume that in the Archean and the Paleoproterozoic, the world was very, very different, and that it was dominated by large doming structures between volcanic cover that produces these, what they call keels, which are the greenstone belts. And I'll talk about this particular view of greenstone belts a bit later on. Other people are much happier talking about modern plate tectonics. There's just about everything in between. In my opinion, we still don't really know the answer to that, which makes it a really interesting thing to study. And I'm sure you can find 10 people at Wits that disagree with me and think they know the answer, but they probably don't all think the same thing. So, mineral deposits. This is the geology of West Africa. You can see that there are lots of gold deposits all over the place. Some areas seem to be particularly rich in gold, like Senegal and Guinea and Ghana, and others have gold deposits, but they're not as big. And then there's also a lot of iron ore, and it has the biggest bauxite deposits in the world in Guinea, and there's diamonds. So it has all sorts of different things. But as I said, we're going to mostly focus on gold because that's where most of the funding came from. So everything I'm going to talk about here, one or two exceptions, is part of a project that we started in 2006 with the 4 people that you see down there, who work for the Institute of Research for Development in France, which was me. It was Patrick Ledru from the BRGM, which is the French Geological Survey. It was Martin Lompo from the University of Ouagadougou in Burkina Faso, and Kim Hein, who was based here at the time. So when we started the project, we managed to get the 10 of the West African Geological Surveys as partners and 12 mining companies. And the funding was coming from the mining companies, and the support, logistical support and access to data was coming from the geological surveys. And it was all glued together by an organization called Amara that I'm not going to explain at the moment. One of the most important things we did was to bring these groups together. These are 3 groups of organizations that often don't work together. So we had the industry partners. They don't work together naturally on their own very much. This is all the industry partners over the last 20 years. The geological surveys, who also don't work together very much, and the universities that have more experience working together, but less experience working with the geological surveys and the mining groups. So all of these groups, something like 80 partners over 20 years, at different times have come together in a series of 4 projects that are called WACS. And probably the most important thing we did in all of this was the training. And so we've been training, built into the project, we have funds from industry to support PhD scholarships, master scholarships, training courses. And this in turn led to a spin-off about 5 years ago of a not-for-profit called Agate that is devoted to advancing African urban planetary science. And it supports, again, scholarships, students attending industry courses, and all sorts of things like conferences. So here's just a picture that I'm not going to go through of the people that have been involved in Agate and its realizing and organization of conferences and things. So Agate is a not-for-profit, but that doesn't mean it isn't a business. All not-for-profits need to make money, otherwise they can't function. And we get our money by running industry training courses. So we run industry training courses, and from the profits we support scholarships and early career grants. And we use some of the profits to bring geological survey people to the courses and local students. And sometimes when we're running a WACSI project, we can get direct funding from WACSI, which takes over the role for the capacity building. And these are the sort of courses we've run in the last few years. So it's everything from structural geology in the field to interpreting geology from geophysics, which was the previous lecture I gave here, doing GravMag inversions, geochemical exploration using QGIS, structural analysis, how to become an exploration manager, also a wide range of things. They have to be of interest to industry because they're the ones paying for it, but then we can use the profits to go and support students. And over the last 20 years, we've managed to train about 170 masters, PhDs, and postdocs. About 2/3 are Africans, and overall, especially when Kim was here, 22 of them were actually at Wits over the years. And what's even better is that now there are 13 different West African institutions that have lecturers that were trained under this program. So those people are now actually getting funding for their research through the later generations of WACSI. The reason I'm here is because I was in Ghana. The reason I was in Ghana was because we just finished running this course on this conference on structural geology and tectonics. So as you can see, it was just 10 days ago. And just because I'm talking about conferences, also in Ghana next year is the Colloquium of African Geology, so in September, I think. So that's something that will be interesting to some of you. And if you want to go even further afield, if you're looking for an excuse to go to Australia, for example, the Society of Geology Applied to Mineral Deposits is having its annual meeting in Perth, where I live, in August, September next year. What we do in terms of research is we try and look at the West African craton on a whole series of different scales, from the scale of the whole thing, and the whole of the West African craton is about 2.5 million square kilometers, so it's a big area, which is why it's covered by 13 countries. We also zoom in to look at belt scales of one greenstone belt. We also look at the deposits, and then sometimes we even look at single arsenopyrite veins. And so let's look at the biggest scale first, which is the craton scale geophysics. These are seismic tomography images, which means that they're horizontal slices through the earth at different depths, 0 to 100, all the way up to 300 to 400, 325 to 400, showing us how fast the S-wave earthquakes were traveling through the material, which we can interpret in terms of the temperature or the composition. And what we can see in particular is that there's this big blob in the shallow part of the system, which is roughly the same geometry as the West African craton. But as you go deeper, it splits into 2 or maybe even 3 what we call roots, which is telling us that perhaps what is now the West African craton originally was made up or assembled from 2 or 3 different blocks. It doesn't prove it, but it allows that interpretation. Geophysics never proves anything.
Yeah.
Neither does geology.
Oh.
So this was not our work, but this is some work that was published just a couple of years ago, where they used ambient tomography to characterize the local, and when I say local, these are 125 kilometer across hexagons, the local crustal tomography of Africa. So I'm just showing West Africa, but the group did it for the whole of West Africa, the whole of Africa. It's a group from Rochester, New York. And they could characterize it into primitive, least modified, moderately modified, and extensively modified crust. And given that, as I've been told by the group, there's virtually no data for West Africa, it's done a phenomenally good job. And so it's giving us a first order idea of what the crust looks like in terms of its at least seismic behavior that we can then interpret in terms of tectonics. As part of WAXI 2, we did this 300-kilometer magnetic telluric survey. When I say we, it was Alan Jones and Florian Lepat. And it's going down 300 kilometers long, and it's about 300 kilometers deep. And so you can see the moho, the base of the crust is up here. The base of the lithosphere is this black dotted line. This seems to show a step in it, at least that's what the way they interpret it. But equally important, the geology at the surface, which is, you can see these big dashed black line shear zones here, have a very strong electrical response going down all the way through the crust and into the mantle. And I'm not going to worry too much how much it goes into the mantle, but it certainly makes us feel as if these structures are at least transcrustal, so they're at least going 30 to 40 kilometers into the crust, which makes them very big structures from what we're mapping at the surface. If we go back and now zoom in a bit, and then I'm going to introduce you to the types of rocks we see. This is the geology map that we produced for West Africa, and I'll talk a bit how we produced that map. The main difference between this map and the previous generations of map is that we used the regional geophysics, so the magnetics, the radiometrics, to constrain the geology because there's only 5% outcrop. So if we relied on the 5% outcrop, we'd probably make a map very similar to the maps made in the 70s and 80s. Because there's more or less complete magnetic coverage and radiometric coverage, we can now make more detailed maps that are constrained by the resolution of the geophysics, not by the spacing of the outcrops. So if we're going to look at this little black area for the stratigraphy, but also just to highlight that these are all different areas where we've done regional studies across the region. And just down at the bottom, that scale bar is 200 kilometers. So they're quite broad studies, and this was a series of PhDs or postdocs. And you can see we haven't been everywhere, and some areas are more broad and more general, and some are more focused. But we're going to look again at this little black area, and this is work of Pat Heyman, who's put together a composite stratigraphy, which is, for the Proterozoic, a pretty classic greenstone belt stratigraphy. It's missing some of the things you see in the Archean, so the greenstone belts that you have in South Africa have a few more things going on than we have in the Proterozoic. But fundamentally, you're going from bottom to top. You have massive and pillow basalts, and then on top of those you get andesitic volcanism. On top of those you get turbidites and some gabbros, and sometimes it reaches the geology reaches the surface and then is submerged again. And then finally you can get some very quartz-rich sediments, some conglomerates. And this is a classical ideal stratigraphy. What's missing, probably the most important, is this sort of more ultramafic lavas at the very bottom of the sequence, which you don't get in West Africa very much. And so this stratigraphy, this is a composite log with one greenstone belt, but we can do the same thing across the craton. So from west on the left to east on the right, Pat has compiled a whole series of these stratigraphic logs. And one of the interesting things about this is that there's some sort of gradient in age of the oldest and even the youngest or intermediate systems. And it's a bit vague, but it's giving us some idea that what's going on in the east is older than in the west. And the other data sets will reflect this, which is why I'm game to put up an arrow or two. So you can see that it's very similar stratigraphies, with sometimes with bits missing, sometimes with additional bits. All of those little numbers in circles are places where we've actually dated the age of the rock, which gives us some sort of pin as to what the age of this stratigraphic column represents. We also have done a lot of work with metamorphism and structure, and so now we're going to look at Ghana, and particularly on the right-hand side, the northwest part of Ghana. And you can see again, very similar sort of stratigraphy that was developed by Sylvain Bloch in his PhD work. And the way he did his mapping was to start with the geophysics and then go in the field. Or sometimes he went in the field and then he looked at the geophysics. It really depended on the day. But here on the left-hand side, we have a composite of 4 different magnetic surveys. Then we have this colored one is just one part of those surveys, the southern part, for magnetics, for electromagnetics, EM, and for radiometrics. And so he had these data with him in the field, and he could go and look at weird things in the geophysics as a way of deciding where he needed to go to try and solve questions that he couldn't solve just with the normal outcrops. But he'd bounce back and forth, and he'd look at an outcrop. And what he did also, which was important, is he went into the field with a handheld susceptibility meter, so you could actually measure the magnetic properties of the rocks in the field. And if you can measure the magnetic properties of the rocks in the field, and you know where you are on the magnetic image, you have a direct and immediate confirmation that what you're looking at in that rock is correlated with the signal that you're seeing in the images. And that's a really effective way of doing the mapping. So he made these petrophysical legends in order to explain how he was thinking about the interpretation. And the way these legends work is that you have each column represents a different rock type, so granodiorite, orphanite, andesite, basalt. He gives the classical mineralogy that he saw in those rocks, the measured susceptibility ranges, the measured uranium, thorium, potassium values, a little map showing what an example of that map of that unit looks like, together with the magnetic image, the radiometric image, and the electromagnetic image. And this is a legend that allows you to go from the raw geophysical data to understanding how the map is put together. And on the left-hand side, you can see his map, and you can see that there's two greenstone belts. There's the Wailaura, there's some big sinistral shear zones on it here, and then there's the Bolin-Agundi with a big dextral shear zone running along there. And that was actually the reason why we went to this area, because it's one of the few places in West Africa where you have two greenstone belts that collide or come together in one map area. So we thought, let's go and have a look. And it turned out to be a fabulous area, lots of outcrop, lots of very complicated geology. And on the right-hand side, a large part of his work was actually pulling apart the metamorphic story. So in this right-hand image, on the left-hand image, the colors mean lithology. In the right-hand image, the colors mean metamorphic grade. So green, not surprisingly, means green schist facies, so relatively shallow. Orange means amphibolite, deeper, and pink means pegmatite, which means quite high-grade metamorphism. And so one of the things he was able to demonstrate for the first time, at least in West Africa, is that these greenstone belts really did have high-grade regional metamorphic aureoles. Up until then, people have typically assumed that anything time they saw amphibolite, it was just a contact metamorphism near a big granite. He was able to demonstrate that there were these big regional high-grade metamorphic systems, and that they were truncated by these major structures, suggesting that those structures may have been involved in the change in metamorphic grade, so that the faults are bringing up one side of the geology relative to the other. And he was able to demonstrate, at least in this area, what the orientation of the major deformation axes were as a function of time. So it started off with north-south shortening, and then that switched into north-south extension, and then it went into dominated by east-west compression. So that's for one area, and of course, each time we did a map in a different area, we came up with a slightly different story, either in terms of the timing events, or in terms of the local stratigraphy or geometry of deformation. This is just one picture. It shows a lowering of normal fault on the left, with increasing metamorphic grade to the left, with a, from this direction, a dextral sets of shear, showing you that we've got some normal fault where the hanging wall is going to my right at least, exposing the deeper crust on the left-hand side. And he also did a lot of detailed petrology and metamorphic analysis to work out what these things are called PT paths, showing you the path of a single rock in terms of pressure on the vertical axis versus temperature on the horizontal axis, producing these clockwise paths which are fairly characteristic of modern tectonics. We also did a lot of geochronology and isotopic studies, and we were able to show that there's changes in the chemistry as a function of time. So in this case, the horizontal axis is time, older to the right, and it's the sodium-potassium ratio, which is showing a significant change in values as a function of time until it reaches some sort of plateau. And then we also did a sort of more spatial analysis of the geochronology, and so we broke it up into 3 blocks, but we've done it in lots of different ways, suggesting that most of the early part of the felsic magmatism was in the east, apart from that little bit with the big blue arrow in Senegal. There was a central time period when kind of you had felsic magmatism everywhere, and then a late period where it was dominantly in the west. And if you put these 3 together and you do it a function of age as a function of longitude, you find that the average migration of this magmatic behavior was something like 3 centimeters a year over 100 million years. So there's some slow variation in behavior over a long period of time. So, and if you add all that up, it adds up to the same sort of tectonic processes being 50 million years younger in the West than they are in the East. Another thing which is Nico Chabot's work, who's also from our lab, is he's taken one of the isotopes, of the lutetium-hafnium isotopes, from these same igneous rocks that they've dated, and if you take the epsilon hafnium, which is giving us the variation in this system, we can get something where we can then contour that, and let's not have an argument about whether we contoured it using the right method, because that comes up every time. But you can see that there are zones which are red, and there are zones which are blue, and the zones which are blue are interpreted as being juvenile crust, which means that they've been essentially directly, the rocks, the felsic rocks, have been directly derived from rocks which are derived from the mantle, whereas the reworked zones are felsic rocks that are derived from rocks that are probably older and they've been reworked tectonically. So we can see this strong pattern, and it correlates pretty well over this side with where we know there's Archean, but it also highlighted that there's an Archean-like signature in eastern Ghana, which is not present in any of the current day geology, but maybe things that we can see under the Volta Basin. So now let's talk about the mineral systems. Here's a whole bunch of deposits. These are all the gold deposits that were in the system. Not that we've looked at all of them, but these are all the major deposits. And you can see that there's several different types of deposits. Most of them are orogenic gold, but then every now and again there's a paleoclasser, and there's some intrusion-related, porphyry copper, skarn, bit of everything. And we can see that the timing of the deposits varies as well, with the youngest deposits in the far west, and the older deposits, the blue ones, more to the east. So this is reflecting what we saw in the stratigraphy. It's also reflecting what we saw in the felsic magnetism. So we have three different data sets suggesting that whatever was happening happened first over on the east in Ghana and happened last over in the west. These are the ones we actually did study over the years. And so we've looked at, and these are, again, some of them are entire PhDs, some of them are 2-week studies, so they're not all the same, but it gives you an idea of the sort of range of different gold deposits we've looked at. And this is their age relationship. So again, the horizontal axis is age, and vertical axis is, they're just sorted by age. And we can see that there's some early deposits which are VMS and porphyries and a little bit of gold. And then there's a whole bunch of later ones. And the other thing that you can see, which is something I've already said, is that the older deposits are, the blue ones are the ones in the west, the black ones are the ones in the east, is that there are no older deposits in the west, and more young deposits in the west. So blue is west, blue is young, black is a bit all over the place, but the oldest ones are only in the east. So again, we're getting this idea, just reinforcing that idea, that all of this is telling us about some sort of tectonics that was a gradual process over 100, 150 million years. So then we get back to the this epsilon map again. So remember, blue means juvenile, and red means reworked. And we can then overlay the deposits on that to see if there's a correlation. And after about 10 years, we went, oh, that's interesting, there's something there. And this is what it looks like after 20 years. And you can see that most of the gold deposits, not all of them, but certainly all the big ones, are at or near these big blue areas. And Where there's a lot of little deposits, it's more in the orange and or into the red. Interestingly, conversely, the diamonds, which are the white diamonds, are mostly in the red areas and very little in the yellow or blue. And some of the dots that are in here are detrital diamonds anyway, so they're not in, we don't know where the source is. And the same for nickel, is that the nickel seems to be concentrated in those very red areas. The nickel are the blue stars. So we have a very coarse targeting tool. So and this is one of the reasons that the companies have been funding us, is because they've been looking at all of those greenstone belts that we saw in West Africa and asking us, why are some of them got gold in them and others very little? And we were sort of throwing our arms around and saying maybe it's near the seduction zone, or maybe it's this and maybe it's that. This doesn't explain why, but at least it gives us an indicator that it's something to do with the provenance of the crust as to whether it's going to be what we call fertile. A fertile rock, meaning it is a rock that potentially can be the source for gold or any other mineralization. If it's infertile, it means that whatever you do to it, if there's no gold in it, doesn't matter how you attack a rock, there's no gold, you're not going to be able to get gold out of it. A fertile rock may be rich in gold, and therefore, if the right conditions occur, you may be able to extract it out of it. So this was kind of the summary from the mineral side, but it leaves some questions. So one way of visualizing all of this was to put it together as what we call a geodynamic atlas, and this is the latest version, where we just have a movie where we put all of the GIS information on in its current position as a function of time. And there are two big problems with this movie. One is that we're doing a lot of guilt by association, meaning that we don't know the age of a Pluton, we assign it to the age of a Pluton we do know that's in the same area, which is cheating, absolutely. And two is that we don't actually know where these rocks were at the time they formed, because they could be two crustal rocks that were 1,000 kilometers apart. But we don't know what that story was, all we know is what's there today. So we can do these analysis, and you can see as it comes around again, starts again at the beginning, that again there's a dominance of magmatism, of early volcanics, of ore deposits, which will start from here, and the early deformation is all in the east, and again you see this migration towards the west. And any data that you have that you can put a plausible date on, you can visualize in this way. And it helped us, it really helped to convince us, even with all those problems that I just mentioned, that there was some sort of systematic variation as a function of time. And you can see that there starts to be this transition towards the west. The only exception to that is up here in Senegal, that seems to have been active the whole time, and that's an important part of the story, is that over the whole history, there's always something going on in Senegal, in Western Mali. So this is every time we publish a paper, we come up with a different model. This was this year's model, literally this year's model. This paper was published 2 weeks ago, and it shows two subduction zones. So these red domains here are one of the subduction zones, and this second one here that runs through the middle is the second one, and honestly we don't quite know where it goes, and that's partly because we haven't done too much work in this eastern side of Côte d'Ivoire. So we have a model now at least, and that's something that we need to test obviously. One of the questions is what's going on relative to the rest of the world, because it's all very well to make a tectonic model, but West Africa wasn't the only continental material that existed at 2 billion years. There were lots of other things that we know already existed. In South Africa, obviously, in Canada, in Australia, all of these bits of continental crust existed, And one of the questions in South America, and one of the questions that people are always asking is the geology of West Africa a direct continuation of the geology of Northeast South America, the Guiana Shield? And the answer is, we don't know. But I'll explain why we don't know in a minute. But the other question, which is really important, is that if we have, let's just go back to the model, 2 subduction zones, why do we have 12 greenstone belts? Because if we're saying that each greenstone belt is not a subduction zone, then we have to have a second mechanism to produce the greenstone belts that are not subduction zones. And so one model which kind of, again, this year's model, which might be useful, is this model of rifting. And on the left-hand side, this is numerical work. It was done by Ibrahim and Ray, Patrice Ray, who's done a lot of this numerical modeling. And what they did is they built 2D models of the crust. So the green is the mantle, the brown is the lower crust, the orange is the middle and upper crust, and the yellow is sediments. And they pulled it. And if you pull it, it doesn't look like they're pulling it, but trust me, they are. And if you do it with today's mechanical properties of the Earth, you get this very localized drifting right in the middle. If you take the same parameters and say, okay, let's see what happens with the same rocks, if you take it back to the Proterozoic, when we all know that the Earth was much hotter, that will change the mechanical properties because it'll change how deep you have to go to get a certain temperature. So these models are MT 600 means that the MOHO temperature was 600 degrees today. That's our estimate of what it is. Back in the Proterozoic, the estimate for what the temperature of the basin MOHO was 800 degrees. So 200 degrees hotter. The hotter the rocks are, the softer they are. And when you pull those ones apart, instead of just getting one rift, you get a whole bunch of parallel rifts. And so one model, and you can call them back-arc masons, doesn't really matter what you call them, but the extensional behavior is the same. And it could be that every greenstone belt that we see, like this cross-section that they showed for Burkina Faso, each of these greenstone belts is one of these rifts that's producing because the Earth crust was hotter at the time. It doesn't solve all of our problems. There's still some things we don't understand, but it's a model that we can go and think about some more. The other question was, how does West Africa relate to the Guiana Shield in South America? So the Guiana Shield is in Venezuela, Guyana, Suriname, French Guiana, and northern Brazil, so just that north part of South America. And we know that 200 million years ago, before the opening of the Atlantic Ocean, they were absolutely in contact. There's no ambiguity there at all, because we have the ocean floor stripes and the transformed zones. There's no question, 200 million years ago they were together. But 2 billion years ago, that's a totally different thing. And here we have 2 recent papers. The top one is using paleomagnetic data, and the paleomagnetic data, the brown is West Africa, the blue is the Amazon craton, and this suggests that they came together at around 2 billion years ago. So they were having their own little life, and about 2 billion years ago they came together. If you look at the just a histogram of felsic magnetism for blue West Africa and red South America, it looks like from 2,240 million years ago to about 2,000 million years ago that they had the same history, and then less than 2,000 years ago their history differed. So they're giving exactly opposite ideas as to how these 2 systems behave. And there's been a number of papers over the years that have proposed, based on geological, paleomag, geophysics, you name it, different methods as to how these 2 continents, bits of continent, fit together. So the black is the West African craton, and this was the very first model, which basically said that it was basically the same at 2,000 million years ago as it was 200 million years. So you close the Atlantic Ocean, and there you have your answer. So that's one end member. And then there's this paper, well, it wasn't even a paper, it was a thesis by Davis from Sydney that put it over here. And then there's a couple of papers recently that put it there. So similar to the first model, but rotated. And then there's a paper that came out recently that puts it over there. And finally, there's a paper that puts it over there. There's only 2 areas left where it could be, so here's your chance to get a paper. There's really, all this tells us is we don't have enough data. So how do we get more data for West Africa? If you want to measure paleopoles, one of the things that we can do is to measure the dikes, the mafic dikes, because they're these big, long, linear features that we can reasonably assume haven't changed their orientation too much from the vertical since they were formed. And so over the years, we've mapped the West African craton and more recently the Amazon craton. And the way we've done this is not by field work, you can never find these things in the field. We've done it by using the airborne magnetic data. I showed you in this lecture, the previous lecture I think it was, these dikes in Mauritania, which were these big magnetic highs all through the area. We've done that for the whole of West Africa and for the Amazon. And in West Africa, we've dated a whole bunch of these dikes. And once we've dated them, the next step is to try and work out what the orientation of the remnants was that tells about where those dikes were in latitude terms when they formed. And so that's some work we're trying to do with Curtin University in Australia at the moment, because they have a new toy. And their toy is a thing called a quantum diamond microscope, which sounds really cool. Quantum diamond microscope, everybody wants one. What it does is it allows you to do in situ measurements of the magnetic response of individual minerals in a system. So you can do in situ, you can look at a magnetite, you can look at a magnetite, and you can work out what the orientation of the remnant vector is within a single grain or even a subgrain of that. And it removes a lot of the ambiguity because just like with in situ geochemistry, when you can see the texture, you can better understand what's providing the signal. And interestingly, if you were here at the last lecture, I talked about this 3D inversion code called Tomofast, and they've modified that code so that it can do inversions of this magnetic field in these thin sections, and they can do really cool things like doing upward continuation by 2 microns. And it's really fabulous, it's really cool. So anyway, the idea is with the curtain is to take some of the dikes that have been dated but don't have poles for, and to try and work out whether these 2 blocks were close together or whether either of them was close together to any other continental blocks at the time they formed. So it's time to stop. Geodynamic setting in the Paleoproterozoic of West Africa, at least, seems to be some sort of transitional period between the Archean and modern plate tectonics. That's not too surprising. It's intermediate in time as well. And the sort of current thinking is that we started off with a primitive volcanism, may have been plume triggered, or it might be a pre-existing Archean plateau, oceanic plateau. We had the formation of 1 or 2 volcanic arcs, and in between them we had either back arcs or wide rifting, which created most of the greenstone belts. I wouldn't put too much money on that one. It still leaves some questions. We then had the convergence of the 2 blocks, and we had thermal relaxation and the final deformation. The same tectonic processes seem to be occurring over a 100, 150 million year period, but older in the east, younger in the west. And the most important gold districts coincide with juvenile crust, as defined by excellent happening. Those are all the people, in fact, they're not all the people, those are a lot of the people that were involved in WAXIs as students or researchers or geological survey or industry. And that's it. Thank you.
Wow, fantastic. Okay, can we have some questions? Go ahead.
You mentioned how the greenstone belts in West Africa, the only part where they don't show a regular stratigraphy is that they don't have an ultramafic phase. Do you know the reason for that?
We think it's because the Archean was hotter, and therefore there were melts that could form with this stronger thermal regime, the hotter regime, that no longer formed once it cooled down. Because if the current moho is 600 and the Proterozoic was 800, the Archean ballparking was probably 1,000. So just that change in temperature is enough to control what liquids can be extracted from the mantle.
Okay, good. Go ahead.
The Pan-African, do you not see any Neoproterozoic or Pan-African overprint?
Well, if I go back many slides, the answer is absolutely yes, but yeah. So here we are in Ghana. This diagonal series of stripes is all related to the Pan-African in Ghana, and then Togo is the inverse. Togo has got a tiny little bit of Paleoproterozoic up here, and all of the rest is either Volta Basin or Pan-African. And Benin, which is the next country after Togo, is mostly Pan-African. The question as to whether there's an overprint on the Perimian, I mean, yes, absolutely there is here. Whether that overprint extends into, it certainly extends into the Volta Basin. Whether it extends into the Perimian, it's really hard to tell. Yeah, I mean, one thing we do know is that, one thing that there is some evidence for is that this big shear zone up here, the Nangombe, somebody did some fission trap work and either side of that big shear zone, and it appears that that shear zone was reactivated during Atlantic opening. So if that was reactivated just because you can see a sort of shift in the fission track, just because that happened in the Atlantic opening means that it probably happened in the Pan-African too, but it's really hard to tell whether things have been reactivated, of course, because you can't date the different phases, because most of the minerals you can use to date faults are very easily reset. So you're very likely to get the last event and not the early event.
I think, if I may ask another question.
Yeah.
Hang on, come back to me. Sorry, I was hanging on to it. It's the ages that you actually, are those the ages of the rocks that the gold is occurring in? I mean, you can't date the gold.
You can't date gold,
right?
no. So, and you can see, if I go all the way forward again, that there's some pretty big bars on the age. That one. You know, some of them go from 2100 all the way down to 2050. So there's an error bar of 50 million on some of these. But even then, you know, so the individual order of these things is completely up for grabs, because, as you said, most of them are really hard to date. The ones that have got narrow constraints, some of them use the Osmian, and occasionally that worked, but sometimes that gave you the age of 2 billion plus or minus 300 million, which is like double the age of the entire system. So it was no use at all. But often we can date the deposit at least at one extreme by having, for example, felsic dikes that cut through the deposit and therefore pin the upper age, and similarly that may have intrusions related to them. It turns out that more deposits than we expected have some sort of intrusion in the neighborhood. Whether it's actually related or not is sort of hard to tell sometimes.
Questions?
On one of the magnetometrics and T models, there were wiggles at the bottom of LAB where you should move. I just want to know, is the limitation of the
program you were using to model the data, or is just data that you can?
No, in fact, what we're showing, that one, is that, you talking about this wiggle at the bottom?
This one, so the side on your left hand side.
This one? Or, sorry, this is a map view, this is a map view, this is the section.
The,
You mean-
the,
What do you mean, this?
The dashed black line or the changes in the blue?
there's a pattern underneath the lab there. Like
Well, where these big squares are. Yeah, I mean, there's, as you go deeper, you get less and less resolution. So at the surface, you'll see that each color square is very small. But with all techniques except for seismic, basically the deeper you go, the less resolution you have. So there's no point in having, can you think of other exceptions?
I was gonna say seismic has that problem too.
No, but reflection seismic compared to all the other
Okay.
ones. It's all relative. But basically, when you're down here, the uncertainty of where of the signal is such that you might as well have a big square because you just don't have the resolution. So that's why we get these bigger and bigger squares. Why it starts to look like a staircase.
Okay, other questions?
I think one of people have to head off to
Their next lecture.
left already.
Okay, well, let's thank Mark again. This has
Thank you everyone for attending.
Good job.
For that.